Hello there. Before talking about my presentation, I wanted to show me simply, since it will be pleasant for the rest of the video. Thanks to the second symposium on machine learning and dynamical systems, it is my pleasure to share with you our work on two methods to approximate the Koopman operator with a reservoir computer. I'm working with my supervisor, Alexandre Mauroy, at the Namur Institute for Complex Systems at the University of Namur, Belgium. Without wasting time, let us get straight to the point. Imagine a nonlinear system that you want to linearize. The classic way is the local approximation provided by the Jacobian matrix computed around some fixed point. But there is another way, which is the global approximation given by the Koopman operator, which linearly describes the evolution of some functions defined on the state space. Following the second possibility, we aim at improving an operator-theoretic method which allows to linearize nonlinear systems. Now it is the moment to lift the veil on the outlines. To start, I will present the Koopman operator in a nutshell and recall a well-known techniques that provide a finite representation of it, the so-called extended dynamic mode decomposition. After that, I will take the time to show you what is a reservoir computer and how to implement it. Then, we will have all our tools to build our two methods to approximate the Koopman operator with a reservoir computer. The following part will be dedicated to results, and before concluding, I will discuss some methods considering results obtained. Koopman operator. The definition of the Koopman operator needs several things. Let capital X be a measurable state space, T be the discretized time, capital F be a dynamical system, and F be a L2 function defined on the state space, unobservable. Then the Koopman operator acts on the observable space and is defined by this equation. This is a linear operator that describes the evolution of any observable driven by the considered dynamical system. For more details, you may read the original work of Koopman, referenced here below. Extended Dynamic Mode Decomposition. The Extended Dynamic Mode Decomposition, EDMD for the close friends, provides a finite dimensional representation of the Koopman operator. But how? Let us consider a set of the observables called the dictionary and an orbit of the dynamical system. Then the Koopman matrix is given by the solution of this well-known least squares problem. For more details, you may read the original work of Williams, referenced here below. And finally, the question at the heart of the problem is about the choice of the dictionary. Indeed, how to choose the best dictionary. Classical methods address this question by choosing some dictionary function a priori. So they use monomials or radial basis functions, for example. But more recently, someone's proposed to train the dictionary using a feed-forward neural network. You can read their work in the reference given here below. Following their idea, we propose to train the dictionary using a completely different neural network, a recurrent neural network with a leaky dynamic and verifying the acoustic property. In other words, the so-called reservoir computer. Let us see what is it. Implement a reservoir computer. Before I start to talk about it, I give you another reference that you can read for more details. The reservoir is made of some internal states, some input nodes, and obviously some output nodes. The dynamic of the internal state is given by the following equation composed of two terms. The second one has two contributions. The first contribution is the internal connections, which are characteristic of a recurrent neural network, since loops are authorized. The second contribution is the input, which is injected in the reservoir through the input mask matrix. The other term in the equation is the leaky integrator that I will explain with more details in the next slide, as well as the different parameters involved in this dynamic. The output nodes compute a simple linear combination of the inputs and the internal states to produce what will be the train dictionary. This notation here denotes the vertical concatenation. Finally, a specificity of the reservoir computer is that only the output weights are computed, while the other weights are randomly chosen in -1, 1. To understand what a leaky integrating neural network is, let us start by studying the leaking integrator. Consider the following Cauchy problem, where k is a constant and a the leaking rate. The solution obtained by the varying constants method is given by this equation. One can easily understand what is behind it by considering two sets of parameters and plotting the solution over the time. For the first example, set the leaking rate and the constant to 1 and start with a null initial condition. The system goes exponentially from the initial condition to the constant k with a leaking rate a as speed. A second example may lead you to buy this affirmation. Keep the leaking rate set at 1, but now the constant equals 0 and the initial condition equals 1. You can see that the system goes exponentially from 1 to 0. You can note that the leaking rate is related to the time needed to go from the initial condition to the constant, and thus is related to the length of memory of the system. Now we can write the continuous time evolution of a leaky integrating neural network as this equation, where c is a global time constant, a is the leaking rate, and sigma is typically a sigmoid, like the hyperbolic tangent, which applies element by element. You recognize the leaky integrator main term here. The second term was the constant, and now it is the value of the activation function sigma, which takes on entry a contribution of the input and the contribution of the internal state. Using the finite difference method with a discretization step delta leads to a discretized system dynamic, which is almost the one of the reservoir. Finally, by introducing alpha as the input gain and rho as the desired spectral radius of the matrix of internal connections, W, we have the expected equation where W tilde is the matrix W with unitary spectral radius. You can note that the spectral radius is chosen such that the reservoir verifies the ecostate property. In other words, the internal state of the reservoir depends only on few previous values of the states, so after some transition time, the states do not depend on the initial states. All our tools are in place. It is the time to use it together to build our methods. two methods to approximate the Koopman operator. The first method we proposed is quite simple. The reservoir states are directly used as dictionary. With more details, you have three steps. The first one is to initialize the reservoir computer. The next one is to run the reservoir with an orbit of the system in the input to generate a set of value of internal state. For that, you just iterate the equation recalled here. At the end of the process, you can build the matrices S and S' given here. Finally, the third step is to apply EDMD on the internal states and compute the Koopman matrix. The latter is the solution of the least square problems introduced previously, and in terms of matrices S and S', it is simply the product between S' and the pseudo-inverse of S. You can note that the Koopman matrix produced with this method is a square matrix of order n plus k, where n is the number of internal states, also called the size of the reservoir, which is typically large, and k is the number of inputs, and so the dimension of the system which provide the orbit injected in the reservoir. Another remark is that there is no use of the output nodes, hence there is no training in this first method. The training is introduced in the second method. There will be a few more steps for the second method that we proposed, but the beginning is quite the same. The first step initializes the reservoir, but also sets randomly the output weights. The second step remains the same as before. Run the reservoir to build matrices S and S'. After that, compute the dictionary values psi and psi' by applying the output weights on these matrices respectively. Then, compute the Koopman matrix given by the product between psi' and the pseudo-inverse of the matrix psi. Once the Koopman matrix is produced, you can train the output weights through one of the two variants described in the next two slides. Finally, you can recompute new dictionary values and loop these alternating linear optimizations until some criterion is satisfied. You can note that the Koopman matrix produced with this method is a square matrix of order L plus k, where k was already defined and L is the number of outputs. So, this second method proposed a trade-off between the quality of the Koopman matrix and its size, since L is typically small. Before presenting the results, let us look more precisely at the output weights training. We propose two variants to train the output weights for the fixed Koopman matrix. For more details, you may read our preprints referenced here below. The first variant is to update the weights. Let us define W such that inputs are some fixed dictionary elements. This definition splits the Koopman matrix into 4 blocks and leads to rewrite this expression. The best weights are the ones that cancel this difference. Imposing that this equals 0 yields the following least squares problem thanks to the Sylvester equation. C1 and C2 are the independent terms. The plus denotes the pseudo-inverse as previously, and the two vertical dots between parentheses denotes the vectorization. The second variant directly updates the dictionary without explicitly compute the output weights. Using W1 introduced at the previous slide and inversing the output equation of the reservoir leads to another expression for the difference we want to minimize. Imposing that this zero yields a partial least squares problem always tends to the Sylvester equation. You can note that this variance is extremely faster than the first one, since the big matrix to inverse is quite sparser. Now, let us get to the results. Results. Is our optimization problem. After applying our two methods and the classical EDMD with Gaussian radial basis functions, we can plot the obtained optimization residue for 5 different systems we considered. In all cases, the proposed methods outperform the EDMD method used with Gaussian radial basis function. In particular, in the case of the Mackey-Glass system, which is a delayed one. The proposed method provides a Koopman matrix that can be iterated to reconstruct the trajectories from the initial condition on the system. Before continuing, it is important to understand that the Koopman matrix is designed to take all the points on the orbit and shift it together of one unit in time. For the reconstruction, we start from the initial condition and iterate. So, it will not be surprising if some error accumulation occurred, since the matrix is not designed for that. These figures illustrate the reconstruction performances of the two methods for the Duffing system. The first method shows a perfect reconstruction, while the second one suffers some imperfections. This new figure illustrates the reconstruction performances of the two methods for the Mackey-Glass system. As before, the first method provided a perfect reconstruction. The second one has some difficulties but remains on the attractor. As a first toy example for prediction, we consider the van der Pol oscillator and verify that both methods correctly predict the trajectory extending training data. For the second state variable, the prediction slowly diverges as the number of iterations of the Koopman matrix increases. Although the dynamics are quite simple, it is noticeable that the classical EDMD method with radial basis functions fails to provide good prediction results. In fact, for all study cases, the predicted trajectory either quickly diverges or converges to a constant. For this reason, we not shown the results obtained with the EDMD method. We now show that the proposed methods are also efficient to predict the trajectory of the chaotic Mackey-Glass dynamic. In the present setting, the first method provides more accurate results for short-term prediction, but the predicted trajectory eventually diverges. In contrast, the trajectory predicted with the second method converges to a constant which is close to the mean value of the data. This can be seen on a long-term prediction. This phenomenon occurs because the Koopman matrix does not have unstable eigenvalues and has only the eigenvalues lambda equals 1 on the unit circle. It follows that the predicted trajectory converges to a steady state associated with that eigenvalue, which corresponds to the average value of the identity observable on the attractor, computed with respect to the stationary density. This value is also equal to the time average of the identity observable along a trajectory, which is close to the mean value of the data. Another aspect of the Koopman matrix that we can study, and finally the one that interests us, is the spectral properties. Indeed, the Koopman matrix can be used to compute spectral properties of the Koopman operator. The eigenvalues of the matrix provide an approximation of the Koopman operator spectrum. Right-angle vectors of the matrix provide the expansion of approximate Koopman eigenfunctions in the basis given by the dictionary functions. Finally, the left eigenvectors are related to the Koopman modes. You can read the reference given here below for more details. Now, we show an approximation of the spectrum of the Koopman operator for the Duffing system and the Rossler one. In both cases, the EDMD method generates many eigenvalues at the origin due to the rank deficiency of the Koopman matrix. Our methods are characterized by less redundancy in the dictionary functions, and in particular, the second method provides a full rank matrix. The second method yields eigenvalues around 1 and inside the unit circle for the Duffing system. It yields more scattered eigenvalues inside the unit circle for the Rossler system. The insets show that the eigenvalues of the Jacobian matrix at the stable fixed points are correctly recovered with the second method. For the Rossler system, the EDMD method also generates spurious eigenvalues outside the unit circle. You can note that eigenvalues with module approximately equals to 10 are not shown in the figure. This explains the fast divergence of the trajectories predicted with the EDMD method. In contrast, the first method recovers the whole unit circle with a few additional eigenvalues inside the circle for both systems. That's it for the result presentation. We can go on with the discussion on the methods. Discussion. The first point approach is the comparison of the methods based on our results. The first method provides the best reconstruction results, since it exploits all the internal state of the reservoir rather than a few linear combinations of them. It should therefore be preferred if one aims at obtaining the most accurate approximation of the Koopman operator. This method is also quite fast since there is no training process. However, the Koopman matrix obtained with the first method may be very large, since the number of internal states of the reservoir computer is typically large. The second method is motivated by a trade-off between the quality of the results and the size of the Koopman matrix, at the cost of an additional computation time due to the dictionary training. It should be considered if one seeks for a low-dimensional approximation of the Koopman operator. In the context of prediction, it also seems that the second method provides slightly better results. While increasing the number of basis functions, the second method should produce results converging to those yielded by the first method. However, the computation time also drastically increases, so that the first method appears to be more relevant and efficient in this case. Similarly, if a large dataset is available, the second method might be computationally demanding because of huge matrices needed for the training. This allows me to continue with strengths and weaknesses of our methods. The strengths are the following. Proposed methods rely solely on linear technique. Both methods require very little data to provide accurate results. Both reconstruction and prediction results obtained with these methods are improved with respect to the results obtained with the classical EDMD method. The Koopman spectrum computed with these methods is consistent and motivates the use of a trained set of basis functions. Now, the two weaknesses are the following. Both methods are not designed for prediction and cannot outperform state-of-the-art prediction methods. A main limitation of the second method is the computational cost of the dictionary training through the reservoir computer framework. Eventually, this is the time to conclude this presentation of our two methods to approximate the Koopman operator with a reservoir computer. Conclusions, perspectives, and references. In this presentation, you saw how the extended dynamic mode decomposition provides a finite representation of the Koopman operator that linearly describes the evolution of observables of a dynamical system. Then, the implementation of a reservoir computer has no more secret for you, in particular for generating dictionary basis functions. Indeed, a learning problem was formulated using the reservoir computer. The results are encouraging since on the considered examples, our methods work better than the classical EDMD with radial basis function. For the next, we propose some perspectives such as improved optimization algorithm for prediction, applications to real systems, formally do the convergence analysis of the alternating optimization. Behind all this work, you will be able to find these references. Do not hesitate to send an email at my supervisor or me if you have any question or remark. Thank you for watching.